What is up, YouTube? In this video, I'm going to give you a step-by-step guide on how to use R to calculate the efficient portfolio. This video is aimed for anyone wanting to get their hands dirty with statistical analysis, getting to learn R, learning about markets, etc., etc. Maybe you want to be a quant. None of this is financial advice, just for educational purposes, but this is the final product you'll build. In this case, I've used Google, Walmart, and Nike to simulate all these portfolios. So every dot is a different weighted portfolio, and you get the Sharpe ratio, the weight of each portfolios, the expected return, and the volatility. And what modern portfolio theory says, to maximize your return, you want to be somewhere on this efficient frontier over here, not this lower bound over here, because this will maximize your volatility and decrease your expected returns. So for example, lately Nike has been doing really poorly. So having a portfolio weight of 96% Nike, 1% Walmart, and 2% Google would give you a very high volatility with very low expected returns. But then again, with a very high percentage of Google, 98% Google, you might have a lot of volatility, but you have the highest returns as well. But then you're looking at the Sharpe ratio, which is your risk adjusted returns, you get the highest portfolio performance over in here, Sharpe ratios of 0.23 almost. And here you see you have about a third of your portfolio in Google, 2/3 in Walmart, and 0% in Nike. Of course, you could use any equities, assets like Bitcoin, gold, but this is of course historic data. There's no reason to think that will happen in the future, but it's a very nice way to get your hands dirty, start analyzing market data. I hope you learn a lot from this video. Let's get started. All right, to get us off to a flying start, I prepared the starter repo, which has all the steps for us to follow along this tutorial and make it as simple as possible. So you can go ahead and check the link in the description. You can go ahead and download the zip file. This will go into your downloads folder, and then choose a folder you want to put it where you can then open it in RStudio. I'm going to put it into the YouTube R folder. So because I'm on a Mac, I'll open up Finder like so. And as you see, the zip file is in my YouTube R folder. Then I go ahead and unzip it, and now it's in my folder. And now the starting template is over here, and we can go ahead and open up RStudio, which is the development environment for R. But now as you're in R, you're going to go over to the top bar and find your session and set your working directory, choose directory. And as you see, I've already set mine to YouTube R. Let's go ahead and check Efficient Frontier Main. And as you see over here in the files on the right, we have our starter file. And to open this file, you'll go over to the file section at the top. You might not see it on my screen, but it'll be in your top bar. And then you're going to go ahead and open a file. This will open up your directory, and you're going to choose Efficient Frontier. For the Efficient Frontier, we're just going to develop. All that it'll have is these comments. So the start of the Efficient Frontier file, the end of the Efficient Frontier file, then we're bringing in some dependencies. So these are libraries we'll use functions from, and then all the steps in these comments. So a hashtag represents a commented line in R. And to kick things off here in R, as we've brought in all these dependencies, we also have to make sure we've installed them in R. So we can open up our console over here at the bottom. And what we're going to do is we're going to run install.packages, and then we're going to create an array of all these files that we need to install. So C denotes an array, and then we're going to just type them in as you see over here. So we have HTTR, JSON, Lite, all the way through the Plotly over here. We press enter, and because I have all these packages already installed, I get a warning, so we won't restart R. So as you see over here, you're just going to let them install the packages. So I'll clip to when this is complete. All right, and like so, all our packages are installed. And to make sure they're all installed, you can go over to packages over here, and you should see them pop up over here. So we have dplyr, for example, over here, and it's checked. If you want to make sure that they are actually checked, you can go ahead and run these lines, and that will make sure that they're checked, but you could also check them over here from the packages. And just as a quick note, why we installed all these packages, HTTR and JSON Lite we'll have to use for our requesting of market data using traditional HTTP request and the JSON data format. Then keyring is where we're going to store our API key so that we don't expose it here in this video. dplyr is something that we use for data manipulation, making data manipulation way easier here in R. And ggplot2 and plotly just going to help us make an interactive chart as you saw in the introduction. So that's it for the setup in R. And now we're going to have to make sure that we get market data. And for that, let's jump into Google Chrome. And we are going to use stockdata.org. There's many sources for market data. You could choose your own, but for this example, we're just going to use stock data because it'll give us a sample set for free. So you're going to just have to sign up. I already have an account, so I'll log in. All right, and as you signed up, you'll come to your account page where you have your API token. I've blurred mine out on the screen, and it's always good practices to keep your own API token safe so no one else can use up your quotas from your account. But what I'm going to want you to do right now is go ahead and copy your API key. So we have that copied. Jumping back into our studio, what we're going to do in our console is we're going to use the keyring library. Keyring. And then we're going to use semicolon, semicolon. And then what we're going to do is we're going to use key underscore set. And what this does, it uses the keyring library and the key set function within it. And it seems like we got an error because we didn't go ahead and define the variable name you want to set. Like so, and then you're going to be presented with a place to present your password. So you paste your API key in over in here. Okay. And now using the same command, but switching the set to get, you'll get access to your API key so you don't have to present it to others. As simple as that. So that's why we did that. And now let's go ahead and look at the API endpoints we can call over at stock data. So we're back over here. Let's go over to the documentation page. Rightio. So we're on the documentation page and they have very thorough documentation, which is very nice for us. And over here, you see the API endpoint. So we can get current stock prices, intraday data, but as modern portfolio theory is based on historical data, this end of day historical data will be of specific interest to us. Let's go ahead and check that. And over here, you can see that this simple endpoint over here will give us the response of historical data as long as we pass some parameters. So of course, we have to pass our API token, but then we can pass the symbols of the stock tickers we want to use. So for example, Apple over here, then we can do the interval, which is defaulted today. We'll just use that. But you can go ahead and look at all these different options, the date from, the date to, how far back you want to go, etc., and you can even sort the data. So all we have to do over here is go ahead and use this endpoint and append the API token, the symbols we want to use, and of course, we will also want to sort it in ascending order. So let's go ahead and copy this from over here, end of day, copy that. Jump into our studio, and over here you see our first step is to get and format price history data. So let's create a request URL variable, and as we need to append the string, we'll use the paste 0 operator. And all these functions, you can always, if you're unsure of how they work, you can go over here to the help tab and paste it over here, 0, and it will give you a definition of how that function works. So in layman's terms, it just bunches everything up together. So let's go ahead and add that initial part of the request URL we just copied. And for all the parameters, we have to add a question mark. And the first parameter will be the symbols will be equal to, and then we'll go ahead and add that as the next parameter. Now for good practices and later on in the code, we'll store the tickers we want to use in a variable. So tickers will be equal to, let's say for example, Meta here. So we'll use Meta Facebook stock as an initial example over here. And over here, we can just append this variable. So tickers. Then, like I said, we're just going to try the sort parameter as well. Let me just paste that over in here like so. Let's close down the console for now so we have a bit more real estate to work with. And as you see over here, I've also added the API token. So whenever you want to add a new parameter, you add the and symbol and then the key name for the parameter, which is API token, and then we add that. So as I said, you can use key ring semicolon key underscore get, and then we pass the name of the variable we set, stock data key, like so. And now we have a request URL which we can send a request to and get historical data for Meta. And what you can always do is you can come to the end of a line. So this line ends over here. And for example, this tickers ends over here. You can press Command Enter, and that will run that line. And over here, you see your environment variables, and we can see that tickers was set to Meta. And now as we set request URLs, let's go ahead and set that. We see that it's been set to this long string we created over here. I won't go too far so you don't see the API token, but you see that the end of day was appended with the symbols equals Meta, sort equals ascending, etc., etc. So that is very sweet. Let's close the console for now. And now we have this request URL we can send our request to. Now, what we're going to do is create a price history response variable, and that will be equal to, using this HTTR package, we're going to get, as it is a GET request. If we open Google Chrome, you see it as a GET request we have to send over here. We jump back into our studio and we just pass in this request URL we just created, request URL. Go ahead and press Command Enter. And now we're running for price history. You can see the stop symbol. And now we have this new line over here, so we know it went through. Let's go ahead and check out what we got. So we have a list of 10, and the status code 200 means that it went through. And then what we want to see is we have the content of this response raw array over here of data. So what we're going to now do is the first bit of processing, we're going to get this raw data, the JSON format of it, and present it in a nice data frame so we can actually read it. So let's go ahead and do that next. Close down the console, open this up a little bit so we have a bit more real estate. So now we have the price history response. So what we're going to want to do is go ahead and get the ticker price data. We'll create a data frame for it. And actually, before we create that data frame, let's just go over and open up the console and show you what the data looks like. So we're going to go ahead and get the price history, and using the dollar operand, we can go ahead and get the content I just showed you. Let's see what this looks like. So you see this raw array. This doesn't give us anything good. So pressing the up arrow, we can get the price history again. So what we're going to want to do is we're going to use the raw to character function. And you see that our raw data is now turned into character data, but this is still quite unreadable for the human eye. So what we want to do is we're going to go ahead and also get from JSON. So JSON is the format of this data. So we're going to add some parentheses over here from JSON like so. So now from JSON, this gives us a nice data frame over here. So we see that we have the meta object over here, but we also have the data object. So this has all the data in ascending order. We have the price data. We have the open, high, low, close, and volume data. Look at this. It's nice to have it over here in the console, but we want to make it a nice data frame. For over that, let's go ahead and get the line from over here that we use. So this gets us all the data, and we see here the dollar operand data. We want to get this data. So let's close this console. So this was give us all the data, but we only want the data, and then using base R, we're going to turn this response into a data frame that we can present very nicely. Data.frame like so. Let's press Command Enter to run this line, and now we have ticker price data over here in our environment variables, and as we open it, we have a lovely data frame. If you're used to Excel or something like that, this is probably way easier for people to read. We have the date, we have the open, high, low, close, volume, and all this data over here. So now we're starting to get somewhere. We have some price data we can start working with. But of course, this is only the price data for one asset, and as we want to manage a portfolio of multiple assets, we want to turn this into a for loop so we can request data for multiple tickers. So first off, let's change this tickers variable to an array. So over here, we're going to change this to include Meta, Coin, Amazon, and NVIDIA. So we're going to run that. You see our tickers variable changes to an array over here. And then we can write a for loop. Let's go ahead and write a for loop. And we're going to call every ticker in our tickers array. So we're going to start off with Meta, and we're going to run all the code inside this for loop. Then we're going to go to Coin, Amazon, and NVIDIA. And actually, now that I think about it, we might actually even need to know the index of the position in the array we're in. So we're going to change this for loop slightly. We're going to go for I in 1 through the ticker's length. So what this will do, it'll run through 1 through 4, as the length of the ticker's array is 4. We can actually try this out. We can, for example, just print 1 or I like so. And if we go to the console over here, we run this, you should get 1, 2, 3, 4, as you see over there. So this code bit is run for each element 1 through 4. So what we can do is we can just get our request URL, paste it in our for loop. And for the tickers, we're going to use tickers I. So in the first run, we're going to use Meta. Second run, we're going to use Coin. Third one, Amazon, and so on and so forth. Then we can pass in these two lines again. They're going to be the exact same, but then we're going to want to create a new data frame, which has all the data. So if we are in I equals 1, so the first iteration of this array, we're going to create this data frame. So all data will be equal to this ticker price data, but we only actually need the date and the closing price. So we're going to pass in a way to figure out we want all the rows and just those two columns. How we do that is like so. So we get the ticker price data, then we add square brackets, and in the first part over here, we leave this empty. That signifies to check out all the rows. And in the second part, we're looking at the columns, and we define the column names we want to use, so date and close. And now the beautiful thing is that if we've gone through this first iteration, we don't have to create the array again, but we're going to go ahead and say all data, so our all data data frame, is going to cbind, so this combines the columns of two different data frames, and we can set the first one to be all data, so whatever we had from the first iteration, second iteration, etc., etc. And then in the next iteration, we'll just use tickers price data, and we're going to get the close price. So we're going to add the dollar operand, and we want the close like so. And now that has all our data in it, if you can believe it. So if I put my cursor over here on the 33rd line, so the whole for loop, run the whole for loop, but unfortunately, we had this conditional set to just one equal. Of course, in conditionals, you have to use the two equal signs operator, and then go ahead and run this again. And let's see what happens. We created a new all data object over here, which should have a similar form to our ticker price data. But now as we open all data, look at that. We have all the data for 4 different tickers. But of course, this is very hard to read because anyone else looking at this without knowing the tickers wouldn't know what each column is. So we're going to go ahead and set the column names as well. And we can do that after the for loop over here. We can go ahead and set the column names of all data to be equal to an array where the first column is, of course, date. And then we can just append, because we have the close price for all of the different tickers, 1, 2, 3, 4, and we have the tickers over here, Meta, Coin, Amazon, and Nvidia. We can add them over here, so our tickers like so. And all this does is now as we open up all data, we have Meta, Coin, Amazon, and Nvidia. So it's a very easily readable data frame. That's a lot of data. And now that's the first bit of data manipulation for you guys. And the first step done over here in getting and formatting price history data. And we can move on to the next bit over here. Very, very cool. All right, so now the next step is for all this data that we have, we want to get the daily returns, and this will allow us to then generate some summary data. So what we're going to do is we're going to, for each of these rows, calculate the daily return. So from over here, how many percent did we go up to get to 204? And for coin over here, how many percent do we go down to go from 77 to 66? And for that, we're going to use the dplyr data manipulation library. So what we're going to do is we're going to create a for loop again. So for each element in tickers, this is what I tried to do at the start, but we changed that to a iteration from 1 to 4. But now we're just going to use E, which represents the ticker name. We're going to go ahead and create a new column name like so, and this is going to be a string because that's not a variable. So this will just create us a column name, for example, meta return. So we can have a column in this all data frame, which has the daily return for each day. Now, for using dplyr, we're going to get the all data frame. We're going to say that we want to use that same data frame, and then we're going to use the pipe operator. You don't really have to know what this pipe operator means. It's basically just then. So we call the all data frame, and then we're going to mutate, which means add a new column or change a existing column. And then using the double exclamation mark operator, we can get the new column name that we just created above over here. So this sets a new column name. And then in dplyr, we set equals to, and then we just want to write a simple equation over here. So we're going to get from our all data frame the column name that is E. So in this case, it'll be meta. And what we're going to do then is we're going to lag by 1. Looks like we have 1 too many parentheses over here. And then what we're going to do with that, we're going to divide. Oh, that parentheses was for the end of the mutate. So like so. And we're going to divide by the same bit over here, 1. So this will give us the expected daily return. Essentially, go ahead and get this price, divide, subtract this price, and then divide by that. So we'll get the daily return and add that to a new column, as we say over in here. So we can actually go ahead and test this out. Let's run this like so. And now as we open up all data, you see that meta return, if we have a percentage gain. So for example, here we had a 2% gain, and for here we had a 14% loss in 1 day over here for coin. That was probably a really bad day for Coinbase for some reason, maybe a crypto market downturn or something else. But essentially now we have the daily returns here in a new column. And what this means is we can take all these values in each of these columns and create a new data frame with the expected returns for Meta, Coin, Amazon, and Nvidia. So let's go ahead and do that. Over in here, let's initialize before our for loop a expected returns data frame. We'll just set it to null, and we'll do the same thing for standard deviation. Like so, we set that to null as well. So now as we have these two initialized, let's just go ahead and make sure we run these. Let's go ahead and that just opens up the console. We can clear that and close that again. Now, as we have the data frames initialized, we can go ahead and get expected returns like so. Again, use cbind, which combines the columns of two data frames. We're going to get the original expected returns, and then we're going to get the mean of the newly created column name over here. As we go ahead and run this, you'll see that we have a new expected returns data frame appear over here in our environment variables, where you see that we have 4 column names. Again, we have to set the column names to the tickers, but you see that the daily expected return is 0.3%, 0.1%, 0.3%, and 0.4% respectively for the 4 tickers that we've set. So we're making great progress. We know the expected daily returns for each asset, but we also want the standard deviations. So we can go ahead and do the exact same thing over here. Let me just paste that in like so. So we're doing the exact same thing, but this time you're using the SD function to get the standard deviation for the new column we just created. And what that means at the end, we also want to add the column names for our expected returns and standard deviations to be the tickers. Boom, boom, boom. And now as we go ahead and run this, and of course we have to make sure we initialize the expected returns and standard deviations to be null. So run that like so. So it seems like we had an error, new column name not found. So we have to, of course, append that to be new column name with a capital C like so. And then we can go ahead and try this again, run that, and everything worked beautifully. We have Meta, Coin, Amazon, Nvidia, expected returns. And over here in our global environments, we should have standard deviations as well. Meta, Coin, Amazon, and Nvidia. So we have the volatility for each of these assets as well, which is very nice as we go along this process of creating the efficient frontier. Now for some extra data, we can go, of course, create the variances and the modified Sharpe ratios. They're very simple to create because we can just use the expected returns and standard deviations data frames for them. So if I go ahead and paste them over in here, like so, we have the variances is of course the square of our standard deviations. So we have the double asterisk denominations to represent a square. So we do that. We get the variances data frame over here. And then in our modified Sharpe ratios, if it is of course our risk adjusted returns, which is our expected returns over our standard deviations. And as they have the same amount of cells, they just divide each other. So it'll be the expected returns of Meta divided by the standard deviation of Meta. So as we run that, we get the modified Sharpe ratios showing us that the higher the number, the better the risk-adjusted returns are. So although that Nvidia over here might have the highest daily returns, the highest Sharpe ratio is Meta. So the risk of the volatility would tend an investor to invest in Meta rather than Nvidia. With all that said, we now have all the daily returns and summary data generated. Let's save the file and we can go ahead and close some of these files. There's lots of them open. It just bothers me seeing them. Like so, those are closed, and we can close down the console as well, and we can move on to our next bit, which is calculating X and variance-covariance matrices. All right, so to get started with this, calculating variance and covariance matrix, which is needed to calculate the volatility of our portfolio, we actually have to calculate an X matrices first. And what this X matrices is, if we look at all the data over here, it will be a matrices with the amount of days we have the expected returns for and a number of columns of the tickers we have. So in this case, it'll be 4 times the 121 entries in this file. And each cell in the X matrices will be the daily return of that asset minus its expected return for the whole period of time. So let's go ahead and do that first. And what I'm going to do is I'm going to paste the formula over here to get this X data frame. And as you can see, we get it from the all data frame. We use square brackets. We subtract the first row, and then we subtract the columns, starting with the first column, which will be the date column, and then the number of tickers we have plus 1. So that'll be the 5th column over here. So we'll only get the rest of the columns. So if we look at what this will look like, XDF, and we get XDF over here, we have Meta return, Coin return, Amazon return, and Nvidia return. So how we're going to do that is we're going to do a for loop of each of the tickers. As we've done multiple times already, you'll be a master in for loops for E in tickers. So we're going to loop through meta, coin, etc., etc. And as I said, we're using dplyr again. So we define our xdf, and then we're going to use the then operator again, and we're going to create a new column. We're not actually going to create a column. We're going to reassign the values in the current columns. So we're going to, again, use the double exclamation to get the column name. And because, of course, they're currently set to returns, we actually want to set the column names of df, column names of xdf, to be equal to the tickers. Over here, we now have meta, coin, Amazon, NVIDIA, not meta return, coin return, etc., etc. And then we're going to mutate that to be equal to, we're going to get the column name, and then we're going to subtract by the expected returns, the first row and the ticker name. So as you see over here in the expected returns, we're going to get, for example, for meta, we're going to get this value over here. And that is as simple as it gets. And now we should be able to run this, and we should see our XDF now have the format of an X matrices that we want. Of course, we have to convert it to a matrix data type. That is as simple as calling X matrix is data.matrix. This is a base R function, and that will just give us a very similar looking. Now we just know that this is a matrix type and not a data frame type, so R can handle it properly. And for the variance covariance calculation, we'll need the transpose of this matrix already, and that is very simple. You just use the T function like so. So now we get the transpose, and we can check that over here. Look at that. We have the transpose of this function. Now, for the variance covariance matrix, which helps us eventually calculate the volatility of our whole portfolio, that is a very simple equation. So what we're going to do is we're going to create that variable will be equal to, let's do first one matrix multiplication, which will be the X matrix multiplied by the X matrix transpose. So that's just going to be X matrix. And then for matrix multiplication, the operand is percentage, asterisk percentage. And then we're going to use the X matrix transpose. And then we're going to go ahead and divide by the number of rows in our XDF minus 1. So that is the simple equation. And as we run this, there's a very simple trick to see if we've done everything correctly. If we look at the variance covariance matrix, very soon we can see we did everything wrong. This should be a 4x4 matrix with the different tickers as the column names and row names. So what we've done wrong over here is we've multiplied them in the wrong order. Of course, matrix multiplication matters, the order. So we have to have the transpose of X matrix multiplied by the X matrix, and this should give us the correct result. So if you run that, now see this, we get a variance covariance matrix, which is beautiful. We have our 4 tickers as both the row names and column names. And to check if this is even correct, we can open up the variance data frame we created earlier. And for meta over here, we see 4495, and if we check out meta 4495, coin will be 2797, and that will be 2797. So that way, this diagonal over here is your variances for each of these coins. But now we have the variance covariance matrix, we are ready to start calculating the volatility for our different portfolio weights. But for that, we can do 2 different things. We can do an equally weighted portfolio, or we can simulate a multitude of different portfolio weights, and then that way check out what would be the best result for a portfolio. But first, let's check out the equally weighted portfolio. All right, so the next step, as I said, expected return and volatility for an equally weighted portfolio. For that, let's create a data frame for an equally weighted portfolio. We can use our X data frame as it should have, as we open up X data frame over here, it has the 4 columns we need, and then we can just take the first row. So it has the space for our equal weights, like so, equal portfolio, as you see over here. And then we can just use dplyr again to make sure that each of these is equally weighted. And how we do that is we're going to go ahead and do a for loop of each ticker, E in tickers, and then we're going to get our equal portfolio, we're going to call it. Go ahead and make sure that each column name, mutate each column name 1 over the length of our tickers array. So that means in this case, each of them will be equal to 25. But if we change the length of the tickers array, we'll get a different amount. So now you see this is an equally weighted portfolio, 25%, 25% coin, 25% Amazon, and 25% NVIDIA. All right. So now as we have that equal portfolio data frame, let's turn that into a matrix so we can do some matrix multiplication with it. And we can, for example, call it weights like so. So that'll just be the same thing, but in a data matrix data format. But now into our equal portfolio data frame, we actually want to add a few columns, our expected return and our standard deviation, which is our volatility, and then of course our Sharpe ratio to see how good of an investment it would be. What we can do is get the sum of the products of each of the weights multiplied by the expected returns data frame. Now as we run this, what you will see in our equal portfolio is that our expected returns for this portfolio distribution would be 0.3% on a daily basis. So essentially what we did is we just took the expected returns. We can take this over here to the side. So each of these 0.035, we multiplied by the weight it is in the percentage, and we added all of them together. So this amount multiplied by this amount multiplied by this amount, and so on and so forth, and all of them added together. So we took the sum product of the weights multiplied by the expected returns. And now for the volatility measure, that is slightly different. And let me just paste it over here, and then I'll talk you through it. So we again take our equal portfolio data frame over here, and we'll add it to a volatility column. So we're creating the volatility column over here, and we're taking the square root of the matrix multiplication of the weights we have multiplied by the variance-covariance matrix we created over here in the previous step. And then we do another matrix multiplication after we've completed this first matrix multiplication, where we do the transpose of the weights. And this gives us the volatility of this specific portfolio weightage. And as we run this, what you will see is that our equal portfolio volatility is 0.02 and our expected return is 0.03. And now as we look at our expected returns, you can see that just by buying Meta or Nvidia, you might have gotten a higher return on your investment just by fully placing your investments in one of these two stocks, as the expected return for a evenly distributed portfolio is less. But we look at the volatility value, which is 0.02, and as we look at our standard deviations, Nvidia, for example, would have had a very high volatility compared to our equally weighted distribution. And then again, Meta has a very similar volatility to our current equally weighted portfolio over here. That's already giving us some information that most likely our efficient frontier will have Nvidia in the top right corner with a very large proportion of our assets in Nvidia, but then a highest Sharpe ratio would be one where Meta had a very high position with the distribution of these four equities. Now we can also add the Sharpe ratio over here, and for that, because we're only dividing the expected returns by the volatility, it is a very simple calculation. We can just go ahead and do the Sharpe ratio is our equal portfolio's expected return divided by the equal portfolio's volatility. As we go ahead and run this, what we see is that our equal portfolio Sharpe ratio is 0.015. And if we look at the Sharpe ratios, modified Sharpe ratios, we see that this equally weighted distribution for these equities might not be that good. As for example, for Meta, the Sharpe ratio is actually higher than our equal portfolio with 0.157, and our modified Sharpe ratio for just Meta is 0.169. But now we get to the good part. We're going to go ahead and do a simulation of multiple portfolios and see if we can get these Sharpe ratios even higher and with what distribution this would work best. All right, for the simulation bit, we'll do this very quickly as we just want to simulate a data frame with as many rows as we want portfolios to test. So we can create a variable to state how many portfolios we want to test. Like so, for example, number of portfolios is equal to 5,000. And then let's go ahead and create a multiple weight data frame, and we'll again use the X data frame as it has all the column names we want. And in this case, it'll also have a length. As you see over here, we define 1 to the number of portfolios of rows and all the columns, and we've set that to 5,000. So if we run number of portfolios first, and then we run multiple weight, you'll see that our multiple weight data frame looks like this. And although there's a lot of NAs over here because we don't have that much data, it doesn't matter as we're going to change all this data to different portfolio weights. And how we do that is we're first going to use a random number generator to generate random numbers from 0 to 1 for each of these columns. And as we've done so many for loops, I'll just paste it over in here. So for E and tickers, we're going to get our multiple weight data frame. We're going to use it, and we're going to call each of the column names, which are each of the tickers, and we're going to use the runIf function, which creates us an array of random numbers between 0 and 1 for as many elements as we present inside the function call as a parameter, and we present 5,000. So this, if we run this, should give us, in our multiple weight data frame, a random number between 0 and 1 for each of the cells in this 5,000 row data frame for Meta, Coin, Amazon, and Nvidia. And because these don't equal to a full 100, we have to create another column which gives us a total of these, and then divide each of these columns by that column to get a percentage from 100 that each of these rows present as a weight of a portfolio. I hope it'll be clear as I go through this code. Luckily, there is a row sums function in R, which gives us the sum of each row. So in our multiple weight data frame, we create a new column called total of randoms, and we do the row sums. If we run that, now checking out our multiple weights, we get the total of randoms over here. So for example, 0.62, 5473, 0.7 is equal to 1.9. And now to get a percentage that each of these represent, we have to divide each of these by the total of randoms, and that will give the weight of each of these assets in our simulated portfolio. For that, what we're going to do is we're going to initialize an empty array for our weight column names, as we'll use that later on in the code, like so. And then we're going to write one more for loop, and let me just paste it over here straight away, and then we'll talk through it like so. So we're doing another for loop. You should be very familiar with these already. And what we do is we define a new column name, which we did at the very start as well. We use paste 0, we take the ticker, and we add weight. So the column name will be, for example, coin weight. And of course, we're also appending these names to our weight column names, as we'll use that later. But then in our multiple weight array, what we do is we call that multiple weight data frame, and then we create this new column name where we get the ticker column, and then we divide by the total of randoms. And this is just a reference to the column name, total of randoms over here. So as we run this, we should get a nice percentage for each asset, but we do get an error because weight column names is not found. We didn't initialize this. We have to run this line of code first, and then we run everything else like so. And now as we look at multiple weight, look at this. We have a equally weighted portfolio over here, with Meta of 31%, Coin 27%, Amazon 37%, and Nvidia at 3%. If we go anywhere down, we could always find a equally weighted portfolio. So 14%, 36%, that's about 50%. And then we have about 8% and about 42% over here, which this will equal 100, 50, and 50. So we've simulated 5,000 possible distributions of portfolio weights over here. But now all we have to do is do the same thing we did for our equal weight. Let's close down the console over here. Our expected return for equally weighted portfolios, where we got the expected return and the volatility, but now we do it for each row in our multiple weight data frame. So let's go over here and jump into the second last section where we calculate the expected return and volatility for our different weighted portfolios. We're just going to go ahead and run through each row of this multiple weight data frame. So for that, we can do a for loop for I in 1, 2, number of rows we have in multiple weight, and then the weights will be equal to a data matrix. So like so, we get our multiple weight data frame, we get the ith row. So for example, first will be 1, and then we'll get the weight column names as the columns we want to use. And if we look at our weight column names, there are meta weight, coin weight, etc., which we have over here: meta weight, coin weight, Amazon weight, etc. And then all we have to do is do the same calculations as we did over here in our equal portfolio weights with the volatility and expected returns. So let's copy these. Let's go ahead and paste them over here. But in this case, we have to change the cell we want to place this calculation in. So what we're going to do is we're going to change this to multiple weight, and because we're going row by row, we're getting the ith row, and we're going to create an expected return column where we put this expected return. And for the volatility, we'll do the exact same thing. We'll copy this and then we'll paste it over here, but we'll create a volatility column. And that is about it. We're very close. So if we run this, that run very nicely. We check out our multiple weight and look at this. We get our expected return and our volatility for each of these simulated portfolios. And then we can start plotting these onto our chart to find the best possible distribution of our assets. Now, final thing to do is calculate the Sharpe ratio, of course, which is very simple. It's just going to be the expected returns divided by the volatility. So that can simply be added over here, multiple weight, and then we use the dollar operand to add the Sharpe ratio by dividing expected return with volatility. Check that that went in the right place. Go all the way to the right, we get the Sharpe ratios. Over here, you can already see you get a 1.9. I saw somewhere 1.9 over here, which is way higher than any of the Sharpe ratios we got with the individual ones over here we did at the very start. So we're doing very well. And the last thing, of course, is changing all of these weights to percentages, the expected returns and volatilities to percentages. Sharpe ratio is a unitless variable, so we won't change that to a percentage, but we can change everything else to percentages. So when we read them, it's way easier to read. So we just have to define all the rows and those columns that we want to change to percentages. So let's do that over in this line. We take the multiple weight data frame, we take all the rows as we don't present anything as the first parameter of the square brackets, but then we define an array of the weight column names and the expected return and volatility to change those into percentages. And that is, of course, very simple. You round this exact same phrase over here by multiplying by 100. And the round function, of course, rounds to 4 decimal points for us to get some significant figures for us to look at. So let's look at that. Multiple weight. Now we have, starting from meta weight, we have 31%, 27%, Amazon weight 37%, NVIDIA weight 3%, and the expected returns on a daily frame is 0.2%. The volatility is 2%, and the Sharpe ratios over here, which are unitless, so they don't as a percentage. But now we have all the data. How beautiful is this? We have the weight of these simulated portfolios in these 4 columns, and then the expected return and volatility, which will be our Y and X axes as we chart these, and then the Sharpe ratios, which will be presented as a color in our chart. So we can move on to the charting portion to find the best possible portfolio over here. All right, so for that, let's go back to our script over here, all the way to the right, remove the console so we have a bit more real estate to work with. Let's give ourselves some space. And now over here, let's generate our graph. So for our graph, we're going to use the ggplot2 library, and we're going to use the ggplot function over here. First parameter it takes is the data frame, multiple weight, or like so. Then it takes the aesthetics that you want to pass to it. So for the x-axis, we'll have the volatility, and then for the y-axis, we'll have our expected returns that we have over here. We can paste those right over in there. And now we also want to add a geom. So the geom we want to add is point, as we want to make a scatter graph. And for the aesthetic of the scatter graph, we'll set the color to be equal to our Sharpe ratio. So if we check out our multiple weight, just say, check out its Sharpe ratio over there. Sharpe ratio, put that over in there. And now we haven't provided any styling, but this is all it takes. So we run this, and we've stored graph in a state variable, and then using Plotly, we can plot this in an interactive way. So using ggplotly, we can go ahead and present our graph like so. And now as we run this, look at that, that generated our expected returns on a nice graph over here with a Sharpe ratio of light blue defining a high Sharpe ratio and black defining a very low Sharpe ratio. So we get the lightest of blues over in here, which has the highest Sharpe ratios. Of course, we don't have any styling here, as you saw at the start. I'll show you how to do that next. But you can see that the lightest blues are over here. The expected returns are about 0.36% a day, and the Sharpe ratio at about 0.2%. Of course, this doesn't show us what the portfolio weights would have been. We have to add these to the aesthetic so we can see how we get to this efficient frontier over here. So let's go ahead and do that. And for that, you don't always have to create your own code. Sometimes there's solutions already out there in the world. So we're just going to go ahead, and we know that we have these dynamically changing column weights that we've stored in the weight columns variable over here, weight call names. So we want to know how to dynamically add those. So the process you'd go through is Google how to dynamically add aesthetics from a data frame to a ggplot. I've already done that. So when I open Google Chrome, I have Stack Overflow open over here, where we have ggplot with aesthetic generated from input data. So if we look at this answer over here, which is the approved answer, they've generated this function which returns a aesthetic that we can add to our plot with our known column names. So we can go ahead and copy that. This will be in the final repository if you just want to check it from the link in the description. But how you would do this, I'm just showing you that you can always reutilize code. So we can take our generate plot function, and this function actually creates the ggplot over in the function as well. But we can just add the aesthetic, which we want over here, which is G on point over here, but we can add it as an aesthetic. So we remove that, and we get this my as, and we can make sure that we return this aesthetic, my underscore aesthetic, and then we don't have to provide the G on point over here. And then the known names, we don't have to hard code in this function, but we can pass our known as from our weight call names function, which will change depending on which tickers we choose. And now all we have to do is, as we've created this function, we can add it to our environment variables. And then over here, we can add it to our ggplot by saying generate plot. We can give our data frame, which is multiple weight, and then we can add our weight call names like so. And now when we do this and run our ggplotly, if we check out over here, in each of these points, we see what weights they refer to. And as we go over here to the very efficient ratio, we can actually go ahead and zoom in over like so. We see that most of them have a very high percentage of Amazon, Meta, and NVIDIA. Double click like so to get away. But now we have all the different weights, and if we go all the way to the bottom, we should see Coinbase over here has a highest percentage. So this gives us a very high volatility and very low expected return. But as we go up the efficient frontier, we see that we have a high percentage in NVIDIA and a very low percentage of coin weight, some Meta in there as well. This gives you the best indication of which portfolio weights you might want to add in your portfolio. Now, the final thing is you could add some styling over here. I can go ahead and add some styling to make it look cool like we had at the start. This will, of course, be in the final repo, so you can check that out over there. But we add some scale colors, the labels, etc., etc. So now as we run this, we should get a nice dark graph like so. And the nice thing is you can open it up in your browser from this button over here. It opened up the browser and you can see this very, very nice graph of modern portfolio theory with our 4 tickers. You can go ahead and analyze this as you wish yourself. But now I'll show you that going into our studio over here, we can go ahead and change the tickers. So if we just wanted to go ahead and check out other stocks, we could go, for example, Google, Walmart, and then finally Nike. Remove NVIDIA from here. So now we have a 3 portfolio distribution. If we go ahead and remove all our environment variables over here, we can go ahead and press Command All and run this whole chunk of code, and it'll automatically generate you the efficient frontier for these 3 equities and this nice graph for you. So it's still running. You can see the stop sign over here, but you see the efficient frontier is created again. You see Google, Walmart, and Nike over here, and the efficient frontier looks something like this. You can go ahead and open this up in your browser again to get a nice view. So that is a very cool way of how you can use R to start your statistical analysis journey in the finance markets. I hope you really enjoyed this video, learned something, and let me know in the comments. This was my first video of this type, doing statistical analysis with R. What other videos you'd like? Should I go more in depth, more high level? I'd be more than happy to try and make videos that you guys want to see. All right, thanks, and I'll see you in the next one.